Okay, so let's jump into this. So today's plan is to review a little bit of the prerequisite material and then start chapter two, particularly sections 2.1 and 2.2. Something that I have done in the past that I started doing a couple of years ago is having a quote of the day. So I have a kind of a little quote or idea each day that I usually try to tie it into something that we're learning, and also hope that it has some kind of broader picture sense to it as well. With math being what we call a general education course, we as a college, we're trying to get better at how we think about general education and how we want you to think about general education. So by general education, we mean a course that's not like, oh, I'm going into an accounting major, like I'm going to do accounting courses or business courses that are very major specific. But these general education courses like math or English or reading or anything like that are, courses that essentially everybody at the college takes. So we're trying to really highlight the fact that these are broad disciplines and they're building a broad base of knowledge for you to build off of. And for that matter, if you decide to go a different route later on, you have a broader base that you can pivot more easily later on. So if you go into accounting and you say, oh, this isn't for me, I want to, do nursing instead, having that broader base allows you to make a bigger pivot more easily. And so the idea of the day today, related to kind of equations in a sense, is the idea of exchanging value for value, particularly in an economic sense, but maybe in other senses as well. It's kind of easy to get scammed these days, especially with so many things being virtual. But if you focus on trying not to get stuff for free, but exchanging value for value, giving one in order to get one, I think that's a good way to approach economics. And in particular, these days, where this might apply is with the rise of artificial intelligence and computers being able to do more and more complex tasks. Each one of us, when we go into a career field and we put our, hang our shingle out, so to speak, and put our name out there and say, I want to work for you in this field doing this task for this amount of money, we have to make an argument that we're exchanging value for value. If we're asking a company to pay us X amount of dollars per year for some service, we have to make an argument implicitly or explicitly, preferably both, that we bring at least that much value to the table. And in some fields, that's becoming more and more difficult. And in some fields, that's becoming easier to do. So when you're thinking of what career path you might want to take or what field you might want to go into, or even what subfield you might want to go into, that's something that kind of, I think, keep in mind is, can you continue for the foreseeable future bringing value to the table? Or is this something where somebody at some point is going to say, oh, I can get a computer to do that. Why am I going to pay you to do that? So I think especially in this kind of computer oriented world where we're looking for efficiency over quality also is another issue. That's something to kind of keep in mind. But then kind of on the other side of that, an idea from Elon Musk, which I know Elon with some of his crazy antics is a little divisive, but as far as a business person, he says a lot of sensible things. But one of his ideas that I heard in a podcast was, respect this idea of exchanging value for value, but don't have a zero-sum mindset. Don't think the only way for you to get more is to take your neighbor's share, but ask, can you kind of grow the whole pie instead of trying to take a bigger percentage? Is there a way that you can bring more value to the table without trying to capture somebody else's slice of the market? So I think it's also an interesting idea. Although the kind of exchange value for value by itself ties a little more closely into what we'll talk about with equations. Okay. So a couple things to recall. So the first idea is variables and expressions. So one thing about math is there are ideas like, how to work with numbers, how to work with fractions and things. There's also terminology, and it actually is important to keep the terminology accurate, to be accurate with the words that we use to describe different mathematical objects. So a variable is really just a placeholder for a number. So placeholder. In theory, a variable could be anything that's not a number. It could be a smiley face or, some fun little picture that you draw or something in theory. But in practice, we don't like to use, crazy symbols like that. In practice, it's almost always a letter. So it might be the letter X or Y, which you're all, very used to. We could have a letter like A or B. We could even, in some contexts, have letters from different alphabets, say like alpha or beta from the Greek alphabet, or maybe omega if we were talking about, say, a wavelength in physics or chemistry or something like that, or gamma, again, used a lot in things like physics and chemistry. So typically our variables are going to be some kind of letter. And in this class, we'll mostly stick to just, American letters or Roman letters. So often we'll use X and Y. We might use other letters in kind of the standard alphabet. An expression is different than an equation. So an expression, it might be something like what we have over here. Evaluate 7x minus 4 for x equals -3. So if I just write down 7x minus 4, this is some combination of variables and numbers, but there's no equal sign. So this is, in a sense, kind of like, in English grammar, kind of like the equivalent of a phrase. It's like, it's kind of an idea, but it's not really a complete idea, in some sense at least. I can evaluate an expression for a particular value of a variable. So I can say, okay, I have this variable x, it's a placeholder for a number. If I just look at 7x minus 4, I don't know what number this will evaluate to. If I put in different choices for x, I get different values for this expression. But I could ask, okay, if I choose the value -3 for x, what does this expression evaluate to? Well, if I choose -3 for x, then I end up with this expression to evaluate. Now, something to note is, as a general rule, if we omit the operation, so add, subtract, multiply, divide, if we just put like 7 right next to x and we don't have a plus, minus, times, or divided by symbol, the implication is multiplication. So this 7x means 7 times x. This 7 directly next to the parentheses -3 means 7 times -3. We have to be very careful with syntax in mathematics. We have to be very careful with exactly what symbols we use when. If I wrote something like this and I omitted these parentheses, well, if I read this, this looks like 7 minus 3 minus 4, or in other words, 0. But this is a different expression, 7 times -3 minus 4. We also want to keep in mind order of operations. The good old PEMDAS, we do parentheses first, exponents second, multiplication and division at the same time, left to right, addition and subtraction at the same time, left to right. So I see here, I do have a set of parentheses, but there's nothing I can simplify in there. Inside of that parentheses is -3. That just is what it is. If it was like, 12 minus 6 or something inside the parentheses, I could simplify that to say 6. But just with -3, those parentheses are just there to distinguish 7 times -3 minus 4 from something like this up here. So just to make sure that we know that that -3 is getting multiplied against the 7. So nothing we can really do at the parentheses level. We don't have any exponents, any of those superscript numbers. We do have a multiplication, 7 times -3. So if I do 7 times -3, well, I have two numbers multiplied together, two integers multiplied together. I have one positive and one negative, which is going to give me a negative result, right? If I have two numbers multiplied together, if they have the same sign, the result is positive. If they have opposite signs, the result is negative. And then the magnitude of the answer is going to be 7 times 3, or 21. So this 7 times negative 3 becomes negative 21. And then the minus 4 copies down. Okay, so we don't have any parentheses exponents. We don't have any more multiplication or division. We do have addition or subtraction. We have a subtraction here. Negative 21 minus 4. I have a negative number minus a number. That's going to give me negative. And then 21 minus 4 is 25. So to evaluate this expression for this value of the variable, that simplifies down to negative 25. So that's an expression, but what's an equation? An equation, or an inequality, is a relation between two expressions. So I might have something like 7x minus 4, and my OneNote loves to correct my 4s to 9s. It tries to close that little top loop all the time. So, but if I have something like 7x minus 4 equals 3x plus 2, in some kind of grammatical sense, this is kind of like making a claim. It's like making a statement that something is true. I'm making the claim that the left-hand side expression and the right-hand side expression are actually the same value. They represent the same numerical value. So an expression is just kind of like a phrase in English, but an equation is kind of like a claim or a statement of fact. And same with an inequality. If I had, 7x minus 4 is less than 3x plus 2, this is also making a claim, making a statement of fact. If I'm imposing, let's say this equation is a statement of fact, then I can still do manipulations, kind of like I did up here, to maybe make things a little simpler or a little easier for me to understand, right? Looking at the number negative 25, that's easier for me to understand and interpret than looking at this big string of numbers and mathematical symbols, right? This is much simpler, much easier to understand and interpret than what we started with. So maybe with this equation, I say this is kind of a complicated equation. It's hard for me to understand and interpret what's going on here. It's hard for me to understand what the value of x ought to be in order to make this a true statement. So I can do manipulations to equations the same way that I did up here, the same way that I did some order of operations and simplified things. I can do the same thing to equations. The most important role of equations is that we have to balance both sides of the equation. If I do something to one side, if I want to subtract 2 from one side of the equation, I have to do the exact same thing to the other side. I have to subtract 2 from the other side. If I want to multiply by 3 on one side, I need to multiply by 3 on the other side. Roughly speaking, I can do anything I want to one side of the equation, so long as I do it to the other side of the equation, and it will maintain that equality. It'll maintain that statement of fact. One little caveat to that is things like multiplying both sides by 0. I mean, okay, you get 0 equals 0. That's still a true statement, but it kind of like destroys all of the information. So there are a few little caveats like that, but those are very much edge cases. So one way that I like to, one analogy that I like, our book uses the envelope analogy. You can also use the empty bag analogy. As you can think that I have, kind of like 2, say, boxes worth of stuff on 2 sides of the scale. I don't claim to be an artist, so you'll have to use your imagination a little bit here. I have 2 boxes on 2 sides of a scale. And I want this scale to balance, and it really doesn't look like it's balanced, but pretend that it's balanced. Tilt your head a little bit, I guess. And if I was thinking of this equation up here, I might think of having, well, let's actually make this a +4 for right now. I might think of having 7x plus 4. So I might have like 4 units of mass over here for the +4. And then I have, let's say, 7 identical bags filled with some amount of mass. So these are bags that are like, you know, like this kind of a thing over here. Now, these bags might have, a half of one of these blue masses in it, each of them for each of them. They might have each of them 3 of those blue units of mass in it. I'm not really sure. On the right side, I have 3 of those same identical bags. And plus 2 given units of mass. Oh, one of these blue for that. And then the question is, in order to make this scale balance out, how many blue units of mass have to be in each of the bags, right? I could see if I put, let's say 2 blue units of mass in each bag, then the left side is going to be way heavier than the right side, right? If I had 2 units of blue mass in each of these green bags, plus 4 more, versus 2 in these 3 green bags plus 2 more, I can see clearly the left side is going to be much heavier because I'll have many more blue units of mass on the left than on the right. But maybe if I put a smaller amount of units of mass in each bag, maybe I could get it to balance out. And that's kind of an analogy, right? All analogies break down at some point, but that's kind of an analogy to what we're trying to do with these equations. As I'm saying, I have a fixed but unknown quantity x, a variable, and I want to know what value of x can I substitute into this equation and maintain that truthful statement. So when I simplify both the left-hand side and the right-hand side expression, I come down to a number on the left side that matches the number on the right side. So maybe I put in a particular value of x and I get -25 equals -25, then that value of x represents a solution to the equation. If I put in a different value of x and I get +12 equals -7, that's not a true statement. That value of x that I substituted to get +12 equals -7 would not be a solution to that equation. Okay, so a couple examples. So let's take a look at this equation. Again, this is a claim about the relationship between 2 expressions. We're claiming that 5x minus 4 and 10x minus 7 are equal. We're claiming that there's a value of x such that if you plug it into the left-hand side and you do 5x minus 4 and simplify that down, and if you do the same to the right-hand side, 10x minus 7, simplify that down, I'm claiming there's a value of x where those 2 sides will be equal. And my question is, for x equals 3/5, is that a solution? If I substitute x equals 3/5 in, do my simplifications, does the left side and the right side, do they equal the same number, or do they end up equaling different numbers? So let's work through that. So substituting x equals 3/5 into the left side expression, and I will put a question mark here because here we're saying, okay, I'm substituting a particular value of x. I'm actually not sure if it's a solution to the equation. That's what we're checking. So I'll put an equal sign, but I'll put a question mark above it just to make it very clear that I'm not claiming these are equal. I'm investigating whether they're equal. Okay, and then I can do PEMDAS. on each side individually. When you get a little more used to this, or if you're used to it now, you can just do kind of both sides at the same time as you step down. But let's do the left-hand side first. So we have a multiplication here. 5 times 3/5. We need to remember how fractions like this operate. 5 times 3/5, a times b over c. I know that this 5 in front really is just a 5 over 1 times 3/5. And I remember that with fractions, when I have two fractions multiplied together, I multiply the numerators together. And then I multiply the denominators together. 1 times 5 is just 5. And then lastly, if I want to simplify this fraction, I note that I have a factor of 5 on the top and a factor of 5 on the bottom. I have a common factor between the top and the bottom, and I can divide those out. So this gives me, I can always think of there being kind of like a hidden factor of 1 in the denominator. I could write this as 3 over 1, or that's just 3. So 5 times 3/5 gives me 3 minus 4. This minus 4 just gets copied down. We did that multiplication. We did that one step in the order of operations. And now we're just left with a subtraction. 3 minus 4 is -1. On the right-hand side, I have 10 times 3/5. Let's come over here to our scratch work for that. Similar to up above, this is going to give me 10 times 3 over 5. And here I note I have a common factor again between 10 and 5. There's a factor of 5 in each of those. 10 is 2 times 5, and the 5 from the 2 times 5 divides out the 5 on the bottom. 2 times 3 is 6. So the question in the first line can be simplified to the question in the second line. That's still a little bit complicated, but if we do 6 minus 7, we see we get a -1. Are these equal to one another? Well, now it's trivially easy to see that yes, they are. And sorry, let me close my email so that it's not beeping the whole class. There we go. So the idea is, in theory, maybe if we were like, robots or something, we could look at this first line and say, oh yeah, those are equal. But that's a pretty complicated task to look at this and just say, are these equal or not? By doing some simplification, I can make my task easier. I can make it trivially obvious that -1 and -1 are the same thing by simplifying as much as I can. And then I can verify that, yes, indeed, x equals 3/5 is the solution to this equation. If I substitute 3/5 in everywhere I see an x here, then the two numbers on the two sides of the equal sign are the same number. The two quantities are the same. Okay, so let's jump over to here and take a look at these first two problems. And I want you to work through these. We'll take maybe 2 or 3 minutes each. So work through the first one, try to work through it on your own. In 2 or 3 minutes, we'll come back together and we'll work through it as a group, and then we'll move on to the second one. If you finish the first one early, then feel free to start on to the second one if you want to. So I'll give you 2 or 3 minutes, and then we'll touch base again. Okay, so does anybody want to say what the first step is? What's the first thing that we would do here?
So the first thing that we would do is plug in like 1/3 and like the x parts.
Exactly, yeah. So we would end up with 3 times 1/3 plus 4. And we want to know whether that is equal to 18 times 1/3 minus 1. So what are each of these 3 times 1/3 and 18 times 1/3, what did those simplify to, those two numbers, when we do the multiplications?
So the first one ended up being 1, like,
Mm-hmm.
and then the second one ended up being 6.
Exactly, yeah. Yeah, perfect. So the fractions can be a little challenging, especially kind of getting back into the swing of things after a break or after a while seeing them, but exactly. So, and we then have 1 plus 4 is 5, 6 minus 1 is 5, and we see indeed this left-hand side equals the right-hand side, and x equals 1/3 is a solution to this equation. So let's take about maybe a minute and a half or 2 minutes and work through the second one. If you want to work ahead, you can start the next one, but we haven't really talked about that topic yet. But we'll work on this one for about a minute and a half or 2 minutes. Okay, yeah, there was a question in the chat. Should we make the 1.5 into a fraction or keep it as is? You could actually do it either way. So you could turn 1.5 into 3/2 and go through and use fractions, or you could keep it as a decimal and do the multiplications as a decimal. So either way would work. You're welcome. Okay, maybe about 30 seconds more. Okay, so what's the first line that I should write down here?
Do we have to like raise our hands or just go?
Yeah, whenever I ask a question like this, it's fine to just talk. And if there are multiple people that all chime in at the same time, we'll deal with that if it comes up.
Well, the first thing I would do is plug in the y equals 1/2 or 1.5 or 1 1/2 or 1.5. So it would be 6 plus 4 times 1.5 equals 2 times 1.5 minus 1. Simplifying, using PEMDAS, you would end up getting 6 plus 6 equals 3 minus 1. Because math and
Yeah.
due to how it due to 6 plus 6 equaling 12 and 3 minus 1 equaling 2, that's a no.
Yep. Exactly. Yeah, that's perfect. So the 4 times 1.5, just to kind of review decimal multiplication super quick, 1.5 times 4, 4 times 5 is 20, 0 to carry the 2, 4 times 1 is 4, that's 6, and we have a total of 1 decimal place, so 6.0, that's where that 6 came from, and similarly for the 2 times 1.5. So if you're not quite up to speed on that decimal multiplication, you can go back and review that in chapter 1. But exactly. So that was a perfect rundown. Is we get down here and we see that if we substitute in y equals 1.5, and we're making the claim that for y equals 1.5, these two sides are equal, we see that that is not a valid claim. Pretty clearly, 12 is not equal to 2. So therefore, this original statement was not in fact correct. So y equals 1.5 would not be a solution to this equation. Okay. So if we're looking to solve an equation, right? So here I kind of gave you the solution and we verified that it was a solution, or in the last problem we did, we hypothesized the solution and saw that it actually was not a solution. We can guess a solution and check, but pretty clearly, if the solution is something like x equals 3/5, what are the chances we're going to kind of guess that kind of random fraction? Probably not very good. I don't really like to guess and check, right? If I had 2x plus 1 equals 3, okay, I could probably guess the answer to that one. If I had this equation, I probably can't guess and check as easily, right? But I have an equation that looks like this. There's just a lot going on. It's going to be really hard for me to guess the correct answer. I'm going to have to spend all day guessing before I maybe happen on the right one. I would like an algorithm, a set of steps that I can use to manipulate this equation into an equation that's easier for me to, quote, guess the solution to. In other words, I would like to take an equation that, looks something like this, do some manipulations to it, and get a result that maybe is something like this, say like x equals 2. Now, there's a technical nuance here that I'll discuss. Well, I'll mention it this once and then not really again for the course. Some folks, some instructors make a much bigger deal of this. And I mean, they do make a fair point. It's a technicality though, so we're not going to focus on it too much. If I write something like this is still technically an equation. I could still ask the question, if I substitute x equals 3 into this equation, x equals 2, if I substitute 3 in for the variable x here, is this a correct equation? Well, no, because then we'd have 3 equals 2. This is still technically an equation that is not solved. And I would have to ask, what can I substitute in for x to make this a correct equation? And the answer is what I could substitute in for x to make this a correct equation is only the number 2. So really the correct way to answer the question, like solve this equation, is to write out a statement something along the lines of the solution set for this equation is brackets 2. So the brackets indicate a set. Again, this is a real technicality, and I think at the level of 080, 090, 108, it's not really worth discussing all of this. However, it is important to note that this is still an equation, x equals 2. I could, in theory, substitute in 3 or 12 or negative 17 for x, and I would see that that's not a valid solution, but I can trivially easily see that substituting in 2 is the only correct solution here. So for our purposes, we're going to say once we get to a, quote, equation that is this simple, where we have a variable on one side and only a number on the other side, we're just going to call that the solution to the equation, right? This is, again, there are some semantics here, there are some technicalities, but there are two things that I want to point out here. Number one is we can move from an equation to an equation. Now, you can't move from this particular equation to this one. This wouldn't be the correct solution, but just in the abstract, you can move from a more complicated equation to a simpler equation that is trivially easy to solve, or in our case, where we'll just say that it's solved. So what I'd really like to do is to similarly to how I manipulated the numbers on each side over here to make them simpler numbers so that I could really easily verify whether the thing I substituted in was or was not a solution. If I'm just given an equation and I don't have a candidate solution to test, and I would like to figure out what the value or values of X that I could substitute in that would yield a correct equation, if I want to figure out what those are, I would like to take this complicated equation, do some operations to it, and turn it into a simpler equation, which I can either say is the solution, or I can say that I can trivially solve. Now, there is a fair point that this idea of solution sets becomes much more important in things like when we start talking about graphing, or when we talk about equations relating to variables, say X and Y. And that's one of the reasons that people make a bigger deal about this idea of solution sets. So this concept of things like solution sets will come up a little bit in the future. So we might, kind of touch on that idea a little bit more there. But at least at this point, we're going to say that an equation that's like, say, X equals 2 or X equals 1.5 or something like that, we're going to just call that the solution to the equation. And I think that's the strategy the book follows too. But again, some instructors do make a much bigger deal about this idea of solution sets. So it is possible that, say, if you get to 108 and you have a different instructor, they might want you to write the answer, more along the lines of something like this. Okay, and then an important idea, where did I say it was up here? The important idea in equations is I can, roughly speaking, do anything I want to the equation as long as I do it to both sides. So, if I wanted to add, whatever, a big heavy weight to the left side, I can do that and it will stay balanced so long as I add that same weight to the right side. If I want to get rid of 2 green bags from the right side, I can do that as long as I get rid of 2 green bags from the left side. If I want to, double everything on the left side, if I want to take each thing that's on the left side and make a copy of it and stick that in the box on the left side, I can do that as long as I double everything on the right side, as long as I take the stuff that's in the box on the right side, make copies of each of the things and stick them in the box too on the right. I can do essentially anything I want to one side as long as I do it to the other side. So the two ideas are, I can do basically anything I want as long as I do it to both sides. And I want to strategically choose what I do to both sides to make my way towards this kind of trivially easy equation, or this basically solved state. So for a problem like this, here I'm using a different variable, just so that we don't think that X is the only variable that's allowed or something. I'm looking to do some operations, to do some manipulations of this equation to get to something like R equals number. Maybe like R equals 5, or maybe like R equals -2/3, or something like that. Right? I want to get here to R equals number by doing manipulations to both sides of the equation. Does anybody want to hazard a guess at what I might want to do to this equation, to both sides, to try to get this left side, instead of being R plus 1/3, to just being an R? what can I do to this left side to change r plus a third, to get rid of that third and to make it just an r?
You can subtract 1/3 on both sides.
Exactly. Yeah. So if I, on the left side here, if I subtract 1/3, then my left-hand side is r plus 1/3. That's what we had originally, minus 1/3. If I add and subtract the same thing, this nets out to 0, and I just get r on that left side. So so we chose to subtract 1/3 from the left side because that got us closer to this state here. That got us r equals, we're good on this side now. That's what we want on the left side. Now the other criterion is I need to maintain equality. So I have 1/2. I subtracted 1/3 on the left. I need to subtract 1/3 on the right. So I chose to subtract 1/3 on the left because that moved me closer to my goal. I then have to subtract 1/3 on the right to maintain that equality. I did something on the left, I need to do the same thing on the right. Okay, now on the right, I have a difference of two fractions. These have unlike denominators. They do not have a common denominator. So, or they're not currently phrased in terms of common denominator, I should say. So I want to come over here and I want to simplify 1/2 minus 1/3. So just a quick review of adding or subtracting fractions with unlike denominators. The first thing we need to do is find the lowest common denominator. I'm going to take each of my denominators, 2 and 3, come over here and scratch work for the scratch work. Exactly, it's going to be 6. Now, the general process will be to get a prime factorization of each of these, but 2 and 3 are already each prime numbers. So the prime factorizations are just themselves. But if we had, say, a 2 versus a 4, well, 4 can break down into 2 squared. That would be its prime factorization. And then I look at my prime factorizations and I see, okay, what prime numbers do I have? 2 and 3. What is the highest power of either of these that I see anywhere? I see a 2 to the first. I see a 3 to the first. 2 times 3 is 6. 2 to the first times 3 to the first is 6. So that's the general strategy. We write down each of our denominators. We get a prime factorization for each of them. We write down each of the prime numbers multiplied together, raised to the power that is the highest power of that prime number we see anywhere in any of our prime factorizations for our denominators. And this is our lowest common denominator. So 6 is the smallest number that's both a multiple of 2 and a multiple of 3. Okay, so now we need to change each of these two fractions into an equivalent fraction with a denominator of 6. What do I need to multiply the denominator of 2 by to get a 6? I need to multiply by whatever was left in this prime factorization. I need to multiply by 3 on the bottom. But I don't want to change the value of the fraction 1/2. So I need to multiply by 3 over 3, which is equivalent to 1. So I've just multiplied by 1. 1 times a half is just a half. I didn't change the value 1/2, but I'm just multiplying it by 3 over 3. And when I multiply the numerators together, that's going to give me a 3. Multiply denominators, 3 times 2 is a 6. So 1/2 is the same as 3/6. For something like this, maybe you could have done that just in your head, but for a more complicated one, we might want to follow the process. We want to do a similar thing for 1/3. My denominator now has a factor of 3 in it, but it needs to supplement with a factor of 2 in order to make a 6. So I need 2 halves to multiply on. And again, I multiply my numerators. 1 times 2 is 2. Multiply my denominators. 3 times 2 is 6. 3/6 minus 2/6, I now have a difference of fractions with the same denominator. I can combine these into a single fraction with the original denominator, and where the numerator now is 3 minus 2. So it's kind of like if I had a pizza that was sliced into 6 pieces, and there were 3 pieces left over this morning, and I ate 2 of them. I have 3 pieces of 1/6 size. Take away 2 pieces of 1/6 size. That's just 3 minus 2, 1 piece that's left. So 1/6. And again, just like with all of this kind of review stuff, I'm going through pretty quickly, like crash course style. If you're thinking, wait, I kind of remember that, but I'm not super sure about that, look back at chapter 1, go through the review, the review section, brush up on these as needed. But we do see that 1/2 minus 1/3 equals 1/6. And this is our solution. So we've gone from an equation where it's kind of hard to tell what value of r we should substitute in to get a true statement, to an equation that we, for our purposes, we're calling the solution. We would substitute in r equals 1/6. If I put 1/6 in for this variable r, I would end up with an equation that is a true statement. And for that matter, I went through and algorithmically determined that this equation up here is equivalent to this equation down here. There's no other value of r that I could substitute in into the quote equation r equals 1/6 other than 1/6 that would give me the solution, right? If I said, does the if I substituted 3 in for r in this bottom squared equation here, if I substituted in 3, is that a solution? Well, no, it's not, obviously. If I substituted in -17, no, it's not, obviously. But that this equation is the same, has the same truth value as the one up here. So pretty clearly, if we substituted 3 or -17 or something in for r all the way at the beginning, those are also not going to represent solutions to that initial equation, because the solutions to the initial equation are the same as the solutions to this equation at the bottom here in the square. And we see that the only solution to this equation in the square is pretty obviously 1/6. So not only did we find a solution, 1/6, we've also kind of implicitly, like in the background, we've argued that it's the only solution, that any other number, 27 or -15/3, or, well, 15/3 simplifies, -15/4, none of those will be solutions. We've showed that 1/6 is a solution, and in fact, it's the only solution to this equation. So by going through this manipulation and finding a solution, we actually kind of implicitly did a little more work than we even thought that we were doing. So let's jump over here and did I think I copied my same my same numbers over. Okay. I had 2 different versions, and I think I copied the same version on both the lecture and the work, but we can change that pretty quickly here. Let's do 7/5 and 3/10. All right. So I'll give you maybe 2 minutes or so to work on this equation. If you want to work ahead, I think I have to adjust this one as well. But if you want to work ahead, we'll jump down to this one similar to this in the lecture next. But take a couple minutes, work through this one, and then I'll adjust that second one as well. Okay, let's work on this one. So what is our first step here for solving this equation?
You want to subtract 7/5.
Exactly. We want to subtract 7/5, and we want to do that from both sides. Now we can write this all out. We can write r plus 7/5, which we're just copying down, and then minus 7/5 equals 3/10, again copying down, minus 7/5. So we can write out kind of explicitly in line exactly what we're doing. When we get a little bit more kind of fluent with working with these equations, sometimes we can just write them underneath and maybe skip this step of canceling out. But right now we see that plus 7/5 minus 7/5, that cancels. And we just get r on the left. And on the right, we get 3/10 minus 7/5. And what does that right-hand side simplify to? Did anybody work through the fractions and get an answer?
You're supposed to find a common denominator, like with the 7/5, which would be 14/10, and then 3 minus 14/10. So 3/10 minus 14/10 equals 11/10. If you want to keep it in mixed number form.
Exactly,
But
yeah.
then-
So we would end up with 3/10 minus the 7/5 would exactly as you said become 14/10. This would give us 3 minus 14 over 10, or negative 11 over 10. And we can leave it that way. We could make this negative 1.1. We could change it into a decimal. We could also change it into a mixed number if we wanted to. R equals negative 1 and 1/10. That would be another option. I tend to stay away from mixed numbers. They have some limited uses, but the syntax is a little wonky, right? Kind of anywhere in math, almost, that we omit the operation, it means times. So if I had like, 3x, that means 3 times x. Or if I have like, whoops, 3 parentheses negative 7, that means 3 times negative 7. In mixed numbers like 1 and 1/10, this really means 1 plus 1/10. So it's a very strange thing. We omit the sign, but in this very specific case where we have a whole number directly next to a fraction, we mean plus when we omit the sign. It's kind of a very strange thing, right? And furthermore, when we have like negative 1 and 1/10, that means like negative 1 plus 1/10. There's even kind of an implied parentheses here. So my personal preference and my kind of recommendation is to try to avoid mixed numbers when reasonably possible. There are some instructors who will say that if you leave it as negative 11/10, that's not simplified. They'll say that to fully simplify it, you should write it as a mixed number. Personally, I don't see much benefit in going through the extra effort to change it to a mixed number, especially when you consider that if you want to do operations with mixed numbers, something like maybe half the time, the process is to make it an improper fraction, to kind of go this way, do the calculation, and then go this way again. It just seems like a lot of shuffling back and forth for not a heck of a lot of gain. If you're doing baking and you have measuring cups, super nice to know, all right, I need a full cup plus a third of a cup or something like. But outside of that, or if you're measuring with a measuring tape or something like, but outside of those couple of niche applications, my opinion is that mixed numbers are more trouble than they're worth. And if you really needed a mixed number, you could just write it like this, right? I mean, just write the extra operation, in my opinion. But I don't know, that's a personal pet peeve of mine, I suppose. So I wouldn't mark anything wrong if you left it as an improper fraction, or if you wanted to write it as a decimal. Now, one other side note, and I'm going through a lot of these tangential side notes today, just as we're kind of kicking off class. So I won't, hit as many of these side notes on a typical lecture, but just because we're, just starting off the whole course, I'm hitting a bunch of these little notes. So one thing, I could use an improper fraction, a decimal, or a mixed number here, but let's say hypothetically, if I had gotten, say, r equals 1/3, would it be right for me to say, oh, well, I'm just going to make that a decimal, r equals 0.3? Here, I wouldn't want to do this. If I have the ability to answer a question exactly, this is an exact answer. I mean, for another problem, but if we got r equals 1/3, that's the exact answer. But really, this is approximate, right? 1/3 is approximately 0.3, but it's really like 0.3333 forever, or we'd say 0.3 repeating. A lot of times it's not easy to enter in 0.3 repeating. So in something like this, it's much better to just leave it as a fraction and do anything you need to do with it kind of as a fraction. But for something like, -11/10 or -3/4 or something, or those convert into decimals very nicely. And then it's, kind of a toss up which one is easier to work with. Sometimes one will be easier than the other times it'll be the other way around. So but just as a general rule in math, if we can answer exactly, we probably ought to answer exactly, even if that means dealing with a fraction instead of a decimal. Unless, of course, the question is asking, round it to the nearest, tenths place or something like that. Then, of course, it's asking specifically for a rounded answer. But as a general rule, if we can answer exactly, we should answer exactly. Okay, so what about a more complicated equation like this one? So here we have a left-hand side expression that's kind of complicated, and a right-hand side expression that's pretty simple, just the number 5. The left-hand side expression is complicated, but it's complicated because we have some like terms that we can combine. We can combine the 4m with the 3m, we can combine the numbers together. The first thing I'm going to do is I'm going to put the like terms together. So I have my 4m, I have a -3m. I need to remember to bring that negative with that term. Then I have a -1 and a +7. And I think I've got all my terms on the left side. I checked them off as I went along just to make sure I got all of them. I didn't copy something twice and I didn't miss anything. And then the right-hand side just copies down. And now I see these first two terms. A term is a structure that is separated by a plus or minus from other structures. So these first two terms, 4m and 3m, they're like terms. They have the same variables to the same powers. In other words, m to the first power. I have 4 amounts of m, 4 of these bags with an unknown amount of quantity in them. And then I take away 3 of them. That leaves me with 1m. And typically when we have a variable that has a factor of 1 in front, a factor is a piece of a component that's multiplied to another component. So like 1 times m, we would say that 1 is a factor and m is a factor. Typically when we have a 1 in front of a variable, when we have a 1 as a factor, we just don't write that 1. So this is just kind of part of what you might call the grammar or the syntax or something of mathematics, just the way that we communicate what we mean in an efficient way. So like if we're multiplying 4 times m, we just don't write times. Or if we have 1 times m, we just don't even write the 1. So we just write m. So 4m minus 3m, we can combine those like terms, and everything from these two terms simplifies to just m. We also have these like terms. They have no variables, they're just constants. So same variables to the same powers, they just don't have any variables. -1 plus 7 is +6 and equals 5. M plus 6 equals 5. And now I've gotten myself down to an equation that looks similar to this simpler one. A lot of the kind of tactics of mathematics, the kind of short-term, you know, what's my like next immediate goal in this problem? A lot of times my short-term goal, my tactics, are aimed at saying, okay, I haven't seen a problem like this before. Can I do something that's legal and legitimate? Can I do something to make this more complicated problem look similar to a problem that I know how to solve? One that I've solved already, like say this one. So by combining like terms, I take this complicated looking equation, I transform it into an equivalent equation, but that I've seen before. I've seen this structure before. I recognize this structure. I know what to do. I subtract 6 from both sides. The +6 and the -6 go away, and I'm left with m on the left side. And 5 minus 6 is -1. I did that a bit faster than we've done it before, but again, as you increase fluency in these areas, you can take some shortcuts. If you didn't catch what I did there, then go that extra step. Do the m plus 6 minus 6 equals 5 minus 6. Simplify things down, and you'll see m equals -1. Our solution to this equation is -1. In other words, if I substitute in -1 up here, simplify everything, the two sides will balance. But also implicitly, I've shown that -1 is the only solution, because this equation and this equation are equivalent. They have the same solutions. And this equation at the bottom clearly only has solution -1. There's no other value that I could substitute in for m where that number equals -1 will be a correct statement. Well, that means that there is no other number other than -1 that I could substitute into the initial equation and yield a true statement. Okay, and then let's look at this equation. So here we have some real PEMDAS going on, some real order of operations going on. And this is where it might start to look a little bit scary, a little bit daunting. But again, what's my goal with this? If I'm getting worried about the kind of strategic side of things, the long-term planning, if I say, okay, I can't figure out what my next 7 steps are going to be right now, can I look one step ahead? Can I do something to this to make it look a little more like, say, this problem? Because I know that I can make this problem look like the, in a sense, relatively speaking, the easy problem. Maybe I can. I have a bunch of parentheses here. What if I deal with those parentheses? What if I use the distributive law for each of these parentheses and then see what I get? Okay, so on the left-hand side, if I distribute 5 into the binomial x plus 2, I get 5x plus 5 times 2 is 10. And then minus 4x, that just comes down. So this 5x plus 10 came from distributing 5 into x plus 2. The minus 4x just copied down. And we're saying that left-hand side is equal to, let's distribute the 3x, and minus 3 times 7 is 21. So this came from that first distributive property on the right-hand side. Now we need to be a little bit careful. We have a -3 times x minus 1. And what I like to do with this is I like to make this a plus -3 times x minus 1, just to remind myself that I'm distributing -3 into each of these terms. So I have a plus -3x, or that's minus 3x, plus -3 times -1 is plus 3. Now, I might have gone through that distributive property a little bit, or those properties a little bit fast. And again, if you didn't catch all of that, I'm speeding up a little bit because we're starting to get close to the end of the time here, and I want to make it to the next section. But you can always go back through and fill in some of these details in your notes. Well, now we just have everything multiplied out, but we have a bunch of like terms that we haven't combined yet. Let me go through like I did up here, put my like terms next to one another, and then combine them. So on the left side of the equal sign, I have 5x minus 4x plus 10. I've used each of my terms exactly once. I checked them off as I was going along, so I know that I'm good. On the right side, I have 3x minus 3x minus 21 plus 3. This 5x minus 4x, those are like terms. I have 5 lots of something minus 4 lots of that same thing. That leaves me with 1x. The plus 10 doesn't really combine with anything, so it just gets copied down. 3x minus 3x, I kind of put 3 of those, bags with unknown quantity in them on the scale, and then I take 3 off. That actually leaves me with 0x. I just won't write that at all on this line. Negative 21 plus 3 is negative 18. And now I've gotten to a structure that I am very familiar with. X plus 10 equals negative 18. I subtract 10 from both sides. The plus 10 and the minus 10 go away, and I'm left with x on the left. Negative 18 minus 10 is negative 28. So even for a problem that looks kind of initially scary like this one, maybe we can't see the whole strategy from the outset. But if we focus on just, can I get one step simpler? Can I do one thing that's that's legal, that's good mathematics, but that somehow gets me a step closer to something I recognize? I can get rid of the parentheses. That's an improvement. I can combine like terms. That's another improvement. And before I realize it, I'm back to my, at least relative to where we started, simple equation. Okay, so let's come over here and work on these 2 equations. So we'll take, I think, about 3 minutes or so for both of these. I think these ones will go a little faster because we don't have so much fraction stuff to deal with. So take about 3 minutes combined between these 2 equations, and then we'll work through the solution. Hopefully my timer didn't startle you as much as it startled me. Okay, so for this equation, the first one, we rearrange our terms so we can see more easily where the like terms match up. And we have 4m minus 3m plus 3 plus 7. And that simplifies down to m plus 10 on the left-hand side. The right-hand side doesn't really have anything interesting going on, so it just gets copied down as that 5. M plus 10 equals 5. We subtract 10 off both sides and get m equals negative 5 as the solution. Coming down to the second one, again, what's the kind of first thing that we can do to make things a little bit simpler, a little easier to work with?
You want to distribute
Exactly, yeah, we want to distribute.
and then combine like terms.
Exactly, yeah, distribute, combine like terms. So distributing gets us to this line. Again, we want to be super careful about distributing that negative 3, making sure that that negative distributes as well. So negative 3 times negative 1 gives me a plus 3. Super easy to miss that negative. And when we get good at combining like terms, we don't always have to rearrange first. We can see that there's a 5x minus 4x is x minus 5. That takes care of everything on the left side. And then I have a 3x minus 3x. Those actually go away. That gives me a 0x, or just contributes 0. And then 9 plus 3 is 12. I want to undo the minus 5 on the left. To undo that, I add 5, which means I have to add 5 to the right, giving me x minus 5 plus 5 equals 12 plus 5 is 17. And again, we've shown that this is a solution to that initial very complicated equation. And we've also implicitly shown that it's the only solution, because this initial equation and this very trivial equation are equivalent. And clearly 17 is the only number I could substitute into the latter equation and make it true. So therefore, it's also the only number I can substitute into the initial equation and make it true. Okay, I think we're going to skip these word problems for right now and maybe come back to it either at the end of class or next week. But one of the really powerful ideas in mathematics, one of the really big ideas that you can take to many other disciplines and many other areas of life, is the idea of generalizing from the specific to the more general case. So suppose that we had an equation like x plus a equals b, where x is a variable and a and b are given constants. They're given real numbers, might be whole numbers or integers or fractions or decimals. Can we find a general solution to this? Can I write the solution x equals something that's related to a and b? So, if a was whatever, 7 and b was 12 or something, I'd want to subtract 7 from both sides. To get x by itself, I want to subtract a from both sides. On the left side, I have x plus a minus a, which is just x. And that equals b minus a. So the general solution to this kind of one-step addition-subtraction equation, x plus a equals b, is to subtract a from both sides and get x equals b minus a. So if you take whatever equation you're looking at, say this one, whoops, went up a little too far. This one, r plus a third equals 1/2. We see that the solution is going to be r equals 1/2 minus 1/3. Going from here to here and just keeping all of our variable names and constant names consistent with what we're plugging in. A would be 1/3, b would be 1/2, and we're using the variable name r instead of x. So we can do this. We can, in general, write down from a kind of standard form of a certain type of equation. We can just write down the solution in terms of the variables and constants that are outlined there. This is a very powerful idea in mathematics that, for whatever values you put in for A and B, this is what the solution will look like. We can do a bunch of problems with specific numbers and then recognize a general pattern, maybe from doing a bunch of those problems, abstract away from the specific details of which specific numbers we were using in those examples, and come up with a general method. Very powerful idea, both in math to solve math problems and in general, life to solve life problems. We go through life and we find that through a bunch of certain experiences that are kind of similar, we can extract a general principle, like maybe say exchange value for value. That might be a good principle for us to use. Or you might go through life and find a different principle that you say, hey, this tends to work well. When I do things this way, it works well. When I do things this way, it works poorly. Maybe being able to extract a general principle from those life experiences that, will help you in the future. Okay, so in the last little over 10 minutes, I want to start into section 2.2. Again, this lecture kind of moved maybe at a slower pace than usual because we had some review to do, a little bit of background from chapter 1 that we covered, and just a few little nuances and technical details about how, I tend to write solutions and things like that. So, the pacing was a little slower this first time because we had some tangential material to cover. So what if I have a similar type of question? If I had a question like r plus 3 equals 9/2, we know how to solve that. But what if I have a problem like 3 times r, or r times 3 equals 9/2? Well, Java wants to make changes to my device. That seems like a no, especially because you're popping up randomly and bugging me. So sorry about that. So if I had r plus 3 equals, say, 9/2, I had a plus 3, and what I would do is subtract 3 to kind of undo that plus 3. I would kind of do the opposite of the thing that's attached to the r to get the r by itself, right? R plus 3 equals 9/2, subtract 3, that gets the r by itself. If I have 3r, let's say it as r times 3 equals 9/2. Well, r times 3, to undo that times 3, what undoes multiplication? Division. So what if I divided both sides by 3? In other words, if I have 3r divided by 3, dividing the left side by 3, equals 9/2. Now, here we have a fraction divided by 3. So we might want to, I guess we could write it as 9/2 over 3, but that's getting pretty complicated looking. But dividing by 3 is the same as multiplying by 1/3, right? Okay, so we can multiply the right-hand side by 1/3. We can think of it that way because that just makes the syntax, the way that we would write it, a little more clear, rather than writing something like 9/2 divided by 3. That's a very jumbled up fraction. It's a little hard to interpret exactly what we mean, especially if we don't make our divided by lines different sizes. So much clearer to write it this way. So 3r over 3, remember this is 3 times r. We have two factors in the numerator, 3 times r. We have a factor of 3 in the denominator. The factor of 3 divides out. We have r over 1, or we'll just call that r. 9/2 times 1/3, we have a product of two fractions. That means we multiply across the top, multiply across the bottom. In the numerator, we have 9 times 1 is 9, and the denominator 2 times 3. And I remember that 9 is 3 times 3, so I do have a factor of 3 that I can divide out of the 9, and I'm left with the remaining factor of 3, because 9 was 3 times 3. One of the factors of 3 in the 9 divided out, but the other one is left behind. And we have, let me get myself a little more space. We have then r equals 3/2 is the solution. So the fraction 3/2 is the is a solution to this equation, and it's the only solution, as I've mentioned before.
I have a quick question.
Yeah, sure.
So in my Math 80 class, when we got to problems like this, I was taught to almost do like the factorization tree. So like writing out the 9 as like 3 and 3,
Mhm.
and then crossing out what's like on the top and bottom. Is that still okay if I do that?
Oh, absolutely. Yeah. Yeah.
Okay.
So that would just be an intermediate step. That's perfectly okay to do. If we wanted to say r equals 9 is 3 times 3 over 2 times 3. Absolutely. Yeah. Anywhere in here, if I skip over a step, or if you want to add in another step for clarity, of course, you're certainly more than welcome to do that.
Okay.
Yeah, but this is just to be absolutely clear, this is kind of what I did in the background with dividing out that 3 from the 9. Okay, so on to the next one. So we kind of have an idea how to solve number times variable equals number. I have a slightly more complicated version of that. So is there anything I can do here to make this slightly more complicated equation look a little more similar to that first one? Well, I might notice here that I have some like terms on the left side, 7m plus 3m. I can actually combine those together and make a 10m. And then the right side is just 5. And now I have, I'm back to a structure that looks like number times variable equals number. I want to get the m by itself. So I have, let's say something like m times 10. And to get rid of that extra times 10, I need a divided by 10, so that the times 10 and the divided by 10 divide out and they go away. So I need to divide by 10 on the left. But again, if I divide by 10 on the left, I better divide by 10 on the right as well. 10m divided by 10, then we're saying equals 5 divided by 10. And again, the factor of 10 on the top and bottom on the left, they divide out. And if I wanted to do one extra step here, I could say that I have a 5 over 2 times 5. 10 equals 2 times 5. And I see that the factors of 5 divide out. Note that when I divide out factors like this, there's always kind of implicitly a factor of 1 floating around. So I wouldn't get m equals 0 over 2. That might be a common mistake, but I would get m equals 1/2. Right. And if we think what would be the realistic, the practical idea here, 5/10, if I had a pizza that was sliced into 10 slices and there were 5 slices left, when I go through my dividing out and all of that, I have half a pizza, right? I wouldn't have like 0 pizza after I did some arithmetic manipulations. When I started with 5 slices of pizza, I wouldn't go to 0 pizza. I would have, half of a pizza overall. So sometimes if you bring things back to kind of the practical side and ask, does this make sense? Then sometimes you'll catch some of those little errors if you mistakenly divided out the 5s and stuck a 0 in the top instead of a 1. You'd see, oh, okay, that doesn't really make a whole lot of sense. But here we have m equals 1/2 as the solution. And I think for the next 3 minutes or so, we'll come over here and work through a couple of these problems. So we'll work through these 2 problems, and then we'll wrap up the last couple of problems next week, and then move on to the next topics. But so let's take 2 minutes to go through these 2 problems, and then we'll touch base, and in the last 2 minutes of class, we will finish them up. Okay, so let's take a look at these two in the last couple minutes. 5r equals 15 over 7. What's the first step that we want to go, that we want to do to solve this equation?
We should divide by 5 on both sides.
Exactly, yeah. Divide by 5, and we get 5r divided by 5 equals 15 sevenths. And again, I'll write this as times 1/5. 5 times r divided by 5, the 5's divide out, and I'm left with r on the left. I have a product of two fractions, so I multiply across the top, multiply across the bottom, and I do see that 15, if I wanted to rewrite that, I could write that as 3 times 5. And these 5's divide out, leaving me with r equals 3/7 as the solution. So this is the value of r, the only value of r that we could substitute into this initial equation to end up with a correct statement. And then what about this second equation? What would be the first step that we would do here?
We would combine the like terms of m, and then from there we would divide the like number, so which would be 6. And we would divide the 6 on both sides.
Exactly. We want to get back to something that looks a bit like this, and we know how to solve that. So we have 6m equals 4 when we do 8m minus 2m. And exactly as you said, we divide by 6 on both sides. M equals 4 over 6. Or we can say m equals 2 times 2 over 2 times 3. Divide out the 2's. M equals 2/3. Okay, so that wraps us up for today. Let me stop the recording.